So let's give it up for
Thank you, and good afternoon. This is the afternoon slot straight after lunch, so if you're going to take a nap right now, please, no snoring, or we'll have to throw you out. Otherwise, I hope what I've got to say over the next 20-30 minutes is going to keep your interest. Coming to a performance conference as an accessibility specialist is something of an interesting challenge from my point of view. So what I would like to do is talk to you about the impact that accessibility has on performance. Web performance, the definition is pretty simple. It's the speed at which we can download and access content in the browser. The time to interaction, the time it takes for all the browser to do its bits and pieces in order that we as users can start consuming and interacting with the content. The browser part of that is pretty well understood, especially here in the Bay Area. Four browsers capture most of our attention, of course, Edge, Firefox, Chrome, and Safari. But what of other users, and specifically those who use an assistive technology like a screen reader? There are screen readers available on every platforms, Mac, iOS, Android, Linux, and Windows. And screen readers have a very close working relationship with the browser. They're practically symbiotic. You can't extricate the two. What one does, the other depends on in many cases. If you're not familiar with screen readers, they are pieces of software that, as I say, exist on pretty much every platform, and they translate what most people look at on screen into synthetic speech, so that someone who is blind or partially sighted can understand and interact with the content. For example,
Heading level 1 using the ARIA current attribute posted in link code links on January 14th, 2017. It is common on the web for the current thing in a collection to be highlighted visually, but providing an alternative for screen reader users has often involved something of a hack. The link ARIA current attribute is intended to solve this problem.
So not the most exciting of things to listen to, but they do the job. If there is content on screen, then a screen reader can translate it into often very synthetic speech. They can also do things that are quite neat, like look at the lang attribute on code to change the way content is pronounced. And the only difference between those two quick examples is the correct lang attribute code for the French sample in the second one. So screen readers really like code. They get a lot of information from it. If we go back in history a little way to the late 1990s, what used to happen is that a document would get loaded into the browser, and both the browser and the screen reader would pass the HTML and create a representation of the document. In the browser, it would be all the things that you're really accustomed to, the DOM and other bits and pieces. In the screen reader, it would be something called the virtual model or the virtual buffer, a completely separate rendering of the document. In some respects, this was quite a good thing. It meant the screen reader could slurp up all the HTML and create a virtual model that enabled it to provide ways of navigating for screen reader users that aren't or weren't available in the browser at the time. On the other hand, of course, it caused a significant dichotomy. We had two user agents effectively passing the same content and quite often coming out with utterly different representations of it. But in terms of the navigation, the virtual model did give us some interesting possibilities. For the first time, it became possible for screen reader users to navigate by different kinds of HTML elements, like headings, for example.
Link heading level 1, regaining site heading level 2 link, playing with the accessibility object Modelio and heading level 2 link, accessible SVG line branch heading level 2 link.
Or pretty much any other kind of HTML element you could think of, like, say, buttons, for example.
Category button collapse, tags button collapse, on other blocks button collapse, conferences button collapse.
So the virtual model made human performance a lot better. Screen reader users no longer had to start at the top of the page and read the content as though it was just a straight, flat text document. They could actually start moving around between different types of content on the page. So the human performance greatly increased with the development of the virtual model in the late 90s. By the time we got to the early 2000s, things had changed. The platform developers, both screen readers and browsers, had recognized that having two different user agents slurp up the HTML and pass them independently probably wasn't the smartest thing that we could have ever decided to do. And so the platforms began introducing platform accessibility APIs. And so the relationship between the screen reader and the browser began to change. Instead of acting more or less independently, now the browser took the HTML and parsed it and did its different representations, and the screen reader then started querying the browser for that information using the platform accessibility APIs. There are at least one, if not more, of these APIs available on different platforms. Windows, I think, has the most. It was the first to introduce the Platform Accessibility API, MSAA, with Windows 95, or an update to it. And it's also got one of the newer ones, UI Automation, which is what Windows 10 and Edge almost exclusively uses, for example. But these APIs exist on every platform, and the screen readers that work on each of those platforms will now use those APIs to query content from the browser. If we take a quick example, we can use the details and summary elements that arrived with HTML5. When we load this kind of code into the browser creates the DOM, creates all the other bits and pieces that we are used to interacting to with JavaScript. And that happens in different ways. In Edge, that has yet to support these elements, the content is just presented in a fairly flat text style. There's no interaction available, it's just straightforward content on the page. Firefox is an example of one of the browsers that does support these elements, and that means it creates the appropriate visual rendering for a disclosure widget, and it also provides the necessary keyboard interaction, another important thing for accessibility. And so it's possible to use this disclosure widget with a keyboard. What happens under the hood is that the browser, when it recognizes that a screen reader is running, also creates something called the accessibility tree. So as well as the visual rendering and the interaction component, it creates a separate tree structure that contains lots of accessibility information about the elements that are shown on screen. So the browser really does get busy with all this information. The screen reader can then query the accessibility tree in the browser for the information it needs to help users make sense of the content.
Tick yellow dot 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 button collapse. Enter. Tick yellow dot 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 button expanded. Makes me happy.
So the information that the browser made available in its accessibility tree enabled the screen reader to query it and say, what are you? And the answer that came back was, well, the summary element is represented as a button in the accessibility layer. It's expandable and collapsible, so its state can change, and its current state is also communicated. So this API-based way of querying information was the way forward for accessibility in the browser. Now here we are in the late 10s, and all screen readers use these accessibility APIs to query the browser. So the browser is now the one that really does the heavy lifting. It's the one that processes the documents, provides the DOM, provides the accessibility tree, leaving the screen reader to take its lead from the browser and simply query the accessibility information therein. So that relationship now has well and properly changed. But it's also had an interesting impact on performance, both in terms of because browser models are changing in the way they process things, but also the constraints and impacts that that applies to the screen readers now trying to query that information from the accessibility tree. So if we look back to how it used to be, there used to be a single processing model in browsers. There was one application process, to give it a simple label, and everything happened in there. The actual application was managed there, all the rendering, the interaction, all the accessibility activity was all handled in the one process. Now, we know, of course, that that really wasn't the smartest idea. So I think IE was the first one to really start moving down this path. Browsers started switching to multi-processing of various formats, where we have a process that looks after the application or the UI, and one or more processes that handle content, and other processes that handle other activities, like visual rendering, for example. Of course, not all things happen in the same ways. On Windows particularly, there are different ways of communicating with the browser if you happen to be a screen reader. You can have in-process communication, which is where the screen reader is allowed to exist within the browser itself and to communicate fairly directly with the content processes inside it. We also have out-of-process communications. This is the typical way it's handled on Linux and Mac and in Windows 10 and Edge at least, on Windows 2, where the screen reader isn't allowed any access to the browser whatsoever. All its communication through the APIs is handled out of process. And it's the difference between these two models that has the most impact in terms of browser and accessibility performance. Naturally, all browsers do things a little bit differently, and of course, the screen readers that work with them also do things a little bit differently. IE, for example, although it technically does do multi-process, is very relaxed in terms of how it approaches that. A screen reader is actually able to inject itself into the application process in IE, but it actually has direct, no-holds-barred access to the content processes. There is nothing getting in the way between the screen reader and its querying of the accessibility tree in the content process. When the screen reader creates its virtual buffer, it's making thousands of calls to create that initial virtual representation of the page. Accessibility APIs are really chatty. There's a lot going on under the hood to retrieve all the information that a page consists of. A simple example is that you query for a line of text, and the screen reader then also needs to know information about whether there are links inside that line of text. If so, what are things like the text inside the link? What's the link's accessible name? Even a tiny little piece of information like that requires a lot of API calls. So on the good side, in IE at least, Windows screen readers are able to access that information very, very quickly because there's nothing getting in the way of those API calls. So the time to interaction, if you're a screen reader user using IE, is remarkably quick because, as I say, there's no proxying of the queries, nothing slowing anything down. The downside, other than, of course, security and all the rest, is that it's remarkably unstable. Anyone who used a screen reader through the late 90s and into the 2000s with IE will tell you that as soon as the screen reader crashed, it would take the browser with it. If the browser crashed, it would take the screen reader with it. And those two things happened on a remarkably frequent basis. So from a stability point of view, this particular model wasn't all that useful, and unfortunately it remains so, but hopefully IE won't be with us all that much longer. I can hope, can't I? I've been saying that since about 1990 something. Chrome and Firefox, on the other hand, do multiprocessing in a slightly different way. They both let the screen reader exist inside the application process, so there's still a fairly close relationship between the screen reader and the browser, but they don't allow access directly into the content processes. Again, typically we've got divergence here too. Both of those browsers manage that relationship in slightly different ways. Chrome was the first one to look into this, and initially what they do was they had the screen reader sit inside the application process, send out a query via the accessibility APIs. Chrome would then take that query, transmit it into the content process, retrieve the information that was needed, send the answer back into the application process, at which point the screen reader would have access to it. This proved to be highly non-performant. It really didn't work. For all of those thousands of calls needed to create the virtual buffer, there was a distinct performance hit, while the browser and the screen reader kind of went through that dance of sending queries and requests backwards and forwards between the two processes. So Chrome changed tack. What they do now is that when content is loaded into a content process, an accessibility tree is created, as I mentioned before. And what Chrome does now is it caches that entire accessibility tree back out into the application process where the screen reader exists. What this means in terms of performance is that there is often quite a slow time to interaction for a screen reader user using Chrome. Those thousands of calls still have to be made to the accessibility tree, but actually the performance hit now comes in the browser's caching of that accessibility tree. Once the caching has happened, performance for the screen reader in Chrome is actually lightning fast. It's superb. But if you're loading a particularly large page, then there is a noticeable delay. So if we take a look at a page that has several thousand links on it and a whole bunch of other content, namely the ARIA spec from the W3C, what we'll notice when you access it in Chrome with a screen reader is that you get your first little piece of information spoken, the title of the page, almost immediately. But then the lag while the screen reader waits for the browser to cache the accessibility tree and then uses that information to create its virtual buffer is pretty noticeable.
Enter. Accessible rich internet applications, Y-Audio 1.1. Total regions, 288 headings and 4,949 links. Accessible rich internet applications, Y-Audio 1.1.
So in days where we now understand that time to interaction delay of more than perhaps a second, it has a pretty detrimental impact on anything from conversion rates to user experience, that nearly 4-second delay is really quite noticeable. Again, if the reward of what you think you're going to get when the page loads is enough, you might hang around to wait for that. But if people are impatient, and we know they are, then that 4-second lag is really quite a significant impact on the user experience. Firefox, most recently, has come to the multiprocessing model more fully when it's moved to Quantum, and it's taken a slightly different approach. In some respects, it's taken its lead from Google's initial attempt, and it lets the screen reader sit inside the application process, and it proxies accessibility API calls into the content process. But what they've done that's different to Google's initial approach is they use something called intelligent caching. So where in Google's initial approach with Chrome, the screen reader needed to make a single API call for every tiny little piece of information, Firefox makes intelligent guesses or assumptions about what other information is likely to be needed based on an initial call. So if the screen reader queries some information about a line of text, Firefox smartly deduces that if the text needs to be known about, then so will all the characteristics of the text, the type of element that it's inside, its other characteristics like font or color, all of those bits and pieces. And it will bundle them up into little small packages and send that back through to the application process. So it's actually on-demand querying, but with intelligent caching that helps reduce the impact that was noticeable initially in Chrome before they switched their approach. So in terms of accessibility performance, it's actually pretty good in Firefox. You don't notice much of a delay in terms of time to interaction, and once the virtual buffer has been created, performance from there on is pretty good too. The catch at the moment with Firefox remains that they didn't quite get the intelligent caching right when Quantum was released. Firefox 57 caused a lot of problems for Windows screen reader users, to the extent that Mozilla made a legacy version available and advised Windows screen reader users, particularly those using JAWS and NVDA, to stick to the legacy version until they'd figured out some of the performance issues around this accessibility layer, caching and querying problem. Latest word I have is that they are getting there. As is always the way with these things, as fast as they uncover some things that needed to change in screen readers, the screen readers identified some more things that needed to be fixed in Firefox. But with fingers crossed, I think we should see Firefox 60 really pulling together this intelligent caching and coming forward with a really good accessibility performance model for screen reader users. Edge, again, takes another approach to multiprocessing. It's probably the strictest of all the browsers out there at the moment. It doesn't allow any in-process communication at all. The screen reader cannot, in any way, shape, or form, inject itself into the browser. So it exists completely separately. And this means it has to send all its API calls via the operating system to the browser. The browser then handles that query and sends the information back to the screen reader user. This means Edge doesn't do anything like caching, so it doesn't cache the accessibility tree. It doesn't do any smart or intelligent bundling like Firefox does. Everything has to be done on a single piece of information per API call basis. That has a huge impact. It means that from a user's point of view, things are pretty good initially because the first call starts returning information and you're pretty much ready to get up and running from the get-go. It does mean, though, that as the screen reader needs to query more information as you're interacting, as parts of the DOM are changing or being reloaded, that performance can get a little bit more sluggish. There's also a catch. Because out-of-process calls are so much less performant than in-process calls, according to Marco Zehi of Mozilla, he estimates about 12 to 50 times less efficient for an out-of-process call than an in-process call. It's meant that initial creation of the virtual buffer is no longer possible. So neither JAWS or NVDA screen readers use the virtual model when they're interacting with Edge. And that's quite an interesting paradigm shift from the screen reader browser relationship. It's the only way to do it. Querying all those thousands of calls needed to create the virtual buffer would simply be impossible. We'd all be there with time to make a cup of tea, probably a sandwich, and come back later to find out what was going on if the screen readers tried creating that virtual model inside Edge or with Edge. Narrator is a slightly different case. This is the integrated screen reader on the Windows platform. It too uses out-of-process communication, but because Narrator is the integrated screen reader with Windows, it's a simple case of kind of when the same organization or the same people working on a product own the whole stack, the kind of integration and the understanding and the operability is generally a lot stronger. So although Narrator has the same constraints in place, of all the Windows screen readers, it's actually the most efficient and performant when it comes to using the Edge browser. If you're curious, this is very much the same situation that we see with Safari. VoiceOver is the screen reader integrated into Apple platforms. And again, because Apple owns the entire stack from the API through to the browser, through to the screen reader on the platform, again, that relationship just works a lot more cohesively together. And so performance there generally tends to be pretty good as well. So what can we do about this? One suggestion is that we drop the virtual model entirely. In the days when websites, web pages were pretty static, we didn't really do much to them after they loaded apart from submit forms, the virtual model was pretty usable. As I say, it enabled a lot of interesting ways of navigating and it made human performance a lot better. In these days where we are constantly changing, interacting, manipulating the DOM, we're moving into an era where we're using the shadow DOM, frameworks like React that I know Marcy's going to be telling you more about later. Those days are kind of long gone. So the question is, do screen readers really need that virtual model anymore? Do they need to ever understand what the whole of a page is doing at any one time? It's an interesting question. So I'll give you a very simple example. If we didn't have a virtual model, a screen reader user would have to do what pretty much every keyboard user has to do if they want to select content, which is to say, hold down the Shift key, keep pressing the down arrow key until you've selected all the content you wanted to, say, copy for cutting or pasting.
Selected. Heading level 2 link regaining site question. Selected. Space. Selected. Posted in. Selected. Link real life. Selected. On October 12th, 2017. Selected. Space. Selected. People often presume I would jump at the chance to be able to see it.
Now sure, that's only holding down a key and pressing another, but that seems like really hard work to me. With a virtual model in place, screen readers are able to introduce really useful techniques that make human performance with content much more efficient. So for example, with one screen reader, you can drop a marker at the start of the content you want to copy, drop a marker at the end, and in a single key press, select everything in between.
Temporary place marker set. Regaining site article. Regaining site article end. Space. Selecting between marked place and current position.
So that kind of interaction, that kind of ease of interaction and navigation from the user's point of view wouldn't be possible without the virtual model. So if we do decide to drop that virtual model, we've really got to make it possible for users to be able to interact and consume content as efficiently as we can possibly make it. If we do drop the virtual model, we're going to need to do some work, and when I say we, I mean the kind of browser vendors and platform owners responsible for the accessibility APIs. They need to be able to do a lot more, or at least screen readers and browsers need to be able to do a lot more with those APIs. So, for example, at the moment, there is no way in some APIs for you to query the next object of a particular type on a page. So that heading navigation we looked at the beginning would be really difficult because there's no concept of saying, give me the next heading on the page so that the screen reader can move focus to it. We need better ways of bundling information together in some APIs. It's all very well if you've got to have a single query for a single piece of information, but even with Firefox's efforts at intelligent bundling, we need better ways of saying, give me this container and everything in it, and all the information about every single element in it in one big chunk, in one API call. There are also some kind of interesting problems with some of the APIs that are perhaps more urgently in need of fixing. A really silly example, but one that's really quite crucial if you happen to be a user, is that UIA, the newer of the APIs on the Windows platform, doesn't allow you as a screen reader user to search content inside an iframe, even when it's pretty much right there in front of you.
Joins find dialog. Find WAD. Add a combo. Right here. Alt+W. Enter. Example Microsoft Edge. Screen find result dialog. Search string not found. OK button.
So if we do look at dropping the virtual model, we really do need the platform vendors, people responsible for the accessibility APIs, to start adding new features and to make them more capable so that the queries that the screen reader sends out to the browser can be done with less calls, much more efficiently, and returning much more useful bundles of information, or indeed, in that case, information that's just simply right there available on the page at all. What can we do as developers? I'm actually going to defer this to Kimberly and Marcy, who are going to focus much more on this in the next two talks. But quite simply, what we can do as developers in terms of performance is code well and code for performance. Almost all of the things that you do to look at performance in the browser at the moment will have a knock-on and positive effect for accessibility performance as well. I do want to say a quick thank you before I leave you with one final thought. These are all the people that very kindly and patiently put up with all my questions over the past few months while I was looking into this topic, because it turns out that accessibility performance in relationship to the browser isn't something there's a great deal of information out there on. So these people I owe an enormous debt of gratitude to for their kindness and their far greater knowledge than I had at my disposal. But the final thought I want to leave you with is that if you've been listening to these screen reader examples and thinking, the experience sounds pretty slow, you're listening to content being read and you're thinking, kind of hurry up, get on with it. Human performance is what this all really comes down to. All the efforts we make in terms of browser performance, accessibility performance, screen reader performance are all in the pursuit of enabling us as humans to do what we do best and to do it as fast and as efficiently as we possibly can. So if you've been thinking somewhere in the back of your mind that using a screen reader is a kind of slow and awkward and cumbersome process, it really couldn't be farther from the truth. When it all comes together, screen reader users with capable screen readers are actually pretty damn good at interacting with content, and we can move pretty damn fast too.
Heading level 1 using the ARIA current attribute posted in link code links on January 14, 2017. It is common on the web that the current thing collection can be highlighted visually, but providing alternative screen readers is often involved something right now. The link ARIA current attribute is intended to solve this problem. Heading level 2.
That's about the speed I tend to listen to my screen reader to on a daily basis. So I'm an impatient person. I don't want to wait for my browser or my screen reader to build the stuff to let me get at it. I just want to consume the content and do it fast and efficiently. So I hope today this has given you some food for thought. Thank you very much for listening.